So I think I am live. Let me see if there is Twitch stream chat. I think it's I'm thinking like if there is a chat box to see any chat that comes in. So yeah, in this video or in this live, so I'm planning to explore neural networks, and particularly in neural networks I'm looking into embedding. So I'll just say what this is. Before that, let's see if the download is done. So I tried Brave today. I was using Brave, and after that I have again tried Brave. So the problem with it is it was not loading my YouTube website, or even if it loads, it's not loading the thumbnails. And also Firefox was much faster for me. I don't know if that's for everyone. So regarding the editor I was using, I actually asked people if which code editor I should use. So most of them voted VS Code. So I guess it's more UI friendly. Okay. Yeah, and I was also saying around 12 a.m., but now it's 12:50. So I actually have the setup, the VS Code setup, and beside that, the program to run the terminal itself. So basically, the Alacrity on the right side and VS Code on the left side. Because I didn't actually like the VS Code's terminal. Alacrity was much useful for me. This is, yeah. Let's give authorization. I don't know people use this or anything else. So what I want exactly is the chat box. Even there's nothing like many chats coming in now, but I just want to keep track of it. Okay, where's the chat? Okay, I guess I'll just look at that because it needs more permissions. So yeah. So I was starting to look into embedding. The basic use of embedding is let me show. So there are different types of classifications or things that neural network does, but what I was doing is I have explored image classification using nets, and also this was more into text based classification, like something is a given text, let's say what type of sentiment is it happy or sad or something. So if that's, for example, if that's the case, then we have to see the only data set we get is the words, right? So for example, you can take the popular tweets sentiment thing. So in that they give the tweets, and we have to classify if what emotion that tweet gives. So if it's happy or sad, I think I have the data set for that. I'll just increase the font in VS Code also. So here we have I think it should be a tweet emotions. Let's see. Yeah, this is the file. So you can see there is a tweet ID, and this is the emotion, and this is a tweet. So the input we are going to give to the network is this text, right? So so the text we are going to, that's the input. So the output, it should guess, or it should predict what class it is. Class in the sense what the emotion the tweet is of. So to do that, we need to do something called embedding. So basically how this happens is, let me show. Yeah, so how this happens, actually there's a Vim plugin for VS Code also, which I am using. So you can see, I'll just show that. This is a plugin, VS Code Neo Vim. So before that we had this Vim plugin, which was not that working because it was not native. So there is this VS Code Neo Vim, which is native and works very flawlessly. So there is emotion.py. So what we are trying to do is, let's say we read the words, right? Let's say take the data set. We read the words, let's say we want, then we should predict the next word, which is to. And if we give want to, then we should predict the next word, which is trade, and so on. So that's what NLP is. I'm just seeing, I don't have 100% knowledge about this, about how to do this. I'm just still very ambiguous about what this is. We can't give the words as an input, right? So in that case, we will be numbering the words. So that's what this does. Embedding does. It is a lookup table that stores embeddings of a fixed dictionary and size. So which means each word is given a number, and that number. So this is I think we don't need this. Let's do something else. So if I import torch.nn as nn, okay, I have to activate the virtual environment. So this takes some inputs. So one is embedding takes in the number of embeddings, which means the size of the dictionary. Let's say the number of words in the dictionary. Let's say there are 3 words. An embedding dimension, the size of each embedding vector. So what does this mean? I think there's a video for this.
So we need to know what all of the labels are. So we can get the list here. And what we're going to do is we're going to create a mapping. We're going to create that mapping from the words to the index. And this is something that I've done for a number of years. This was typical pre-Pandas days when you would use a list of columns, and you'd have a dictionary, and that dictionary would tell you what the name of each column was, or a list of rows.
So this is what that dictionary is, the n-grams. So you can see this is this big dictionary here, and if you see this part, we have this numbering. Let's say make has 0, cold has 1, old has 2, and so on. So that's the complete dictionary of words that will be used in the given data set. So if a new input comes in, so it picks up words from this and predicts the next word, right? So let's actually open ChatGPT if it's online. I don't know if it's online. Yeah, it's online. They want to ask what is this in Pytorch embedding. So it refers to the dimension of embeddings or the size of the vector representation of each word in the vocabulary. Okay, so here we are giving, in this case they're taking the class input as the embedding dimension.
Expect that in the future. Very small, and we can sort of forget about it for the moment. We can set it aside. So now we have our model set up. Now the only question is how do we actually execute that forward pass? Because we might have more complicated logic. In our case, we don't, but we might.
Okay, he has this constant, I guess,
So
which is
if you thought about,
so embedding dimension is 2 and the context size is 2. So let's listen actually to that.
That's not the main focus of mine. So some baselines that we'll get started. We're going to just do a baseline import. Nothing that's too exciting here. We won't go through every detail, but effectively you're typically bringing in both the full Torch library so you can get access to everything internally, and then setting up the neural networks versus functional versus the optimization functions. Again, you don't need to have all of these. You can preserve with just the Torch and just fill these in with the dot, whatever you need, but this is pretty standard. Now, we're going to be talking about an example that is NLP based, and they're going to be using Shakespeare sonnet number 2. When they're talking about context size, what we should think about here is the problem, the actual business problem that we're trying to apply, is can you, by knowing the first 2 words, predict the third word? So in a sequence, in a rolling window that starts at the beginning of the sonnet, we know the first word.
Okay, the context size is, let's say, window size. So as we were saying, if we know the first 2 words as an input, we have to guess the third word, right? So maybe the context size is that 2 words we are selecting. So the number of words we are selecting.
So that is when 40. Can we predict that the next word that should occur is winters? When we know the words 40 winters, can we predict that the next word should be shall? When we know winter shall, can we predict that the next word should be besieged? And a couple of things we should note. First of all, we can see it's a very small amount of data, right? Our test sentence is just... The second point is that we're making an assumption that actually is pretty true in terms of line. We're going to represent each word in this sentence in a 10-dimensional space. So each word, instead of having a value, as though you were doing clustering, like 1, 2, or 6, each word will have 10 dimensions that describe it. So it'll be a vector, in this case a tensor, of length 10, and that those 10 values will represent the words that exist. So what we'll do is we'll get these in.
Okay, let's try that. Okay, I think my keyboard's not working. Yeah. So it has, if you do it with context size as 2 and window embedding dimensions as 10, so we have this class. So if we do e.weight, it gives us some random weight. whenever we initialize this, so it will you know, calculate the loss and then um, apply that loss to itself, and then recalculating the weights. So as then that's called basically training, right? So because we gave 2 comma 10, so there is this 10 dimensional vector space, which means we have 10 elements here. That's one array, and we have two 10D arrays. So it's basically 2 into 10, but the 10 is an array. It's a list of itself. Oh, that's what is.
And so forth and so on.
Let's actually do what he's doing here. I think there's a repo for that. Yeah. So there is this engrams. So before that, we need some input. Let's take this test sentence as input itself. So if we do sentence, yeah, we have an array of words. So we have to now map those words. Okay, is to embedding dimension is 10. So we have this complete list. So what this actually shows is if there is 40 and when, then the next word should be winters. If there's winters and 40, then the next word should be shall. So we are actually taking this from this input. So we can see when 40 is there, then winters is the next word. 40 winters is there, then shall is the next word, and so on.
And think about the full space of possible results, but we're going to be thinking about the list of all possible vocabulary words that are available.
Yeah.
These, in fact, are our labels. So we need to know what all of the labels are. So we can get the list here.
So vocab is
and what we're going to do is
unique words which are in this test sentence.
From the words to the index. And this is something that I've done for a number of years. This was typical pre-Pandas days when you would use a list of columns. And you'd have a dictionary, and that dictionary would tell you what the name of each column was, or a list of rows, if your rows had names. Same way. In this case, what we're doing is we're assigning
so you can see we are
to each of the words.
So you can see we have this each number assigned to a word. So now onwards, if we are going to give an input to the network or to the neural network, we won't be giving the word, but we will be giving the number representation of the word. So let's say we are going to give the input as child succession, then we are going to give 1 and 2 in a tensor representation.
It's in our vocabulary. So we have, it looks like around 95, 96 different words in our is to think about importing this neural net module and then building an instance of that. And really what we're going to do often is overwrite just the core functionality of the embedding size tells us the number of columns. Each word will correspond to a size of an embedding. And the context size will tell us how many words go into that embedding. And so when we look down here, we'll see that the embeddings.
So my doubt is if the embedding dimension doesn't depend on the vocabulary size.
We have a neural net embedding layer. And then embedding layer will take in the vocabulary size. So each embedding layer will take in the total range of possible words, and it will output
embedding layer will
the
take in
embedding
the total
dimensions.
range.
Those are the vector, a 10-dimensional vector in our case, a dimensional tensor, that represents the word that we're interested in. So if you think about this as a matrix, it's not quite represented that way, but if you think of this as a matrix where each of the words is its own row, then you have a 96 by 10 embedding dimension. Well, if we have two words, 1 and 2.
Hey guys, do you know, like, okay, it has built-in chat, I know that, but I want the box to pop out. So it was there is this thing, there's a chat box thing, right? So the chat box comes out of the website, so I was looking into that actually. I know the chat is here, but chat, I don't know how. I mean, I have never done it. I have no idea how to do that. So I have downloaded this Streamlabs, but I don't know if that's going to give any chat box kind of thing. Okay. Okay, it's here. Okay. I think this is good. I think this is good enough. Like, I have the chat here.
Each of which are 10 dimensions. Then when we combine them, we need to bring in both the context size, that's the number, how many words, and the embedding dimensions. So 1 and 2 words multiplied by 10, of course, is 20. So we're going to take in our first layer of our neural net, we'll take in a 20-dimensional tensor and convert it into 128 dimensions. Really important. We're going to take each word, embed it in a 10-dimensional space. Then because we're using 2 words as our context size, we're going to take those 2 words and concatenate them together, bring them together. And those 2 words that are concatenated together are going to start at 20 dimensions, and they're going to move to 128. And then in our particular example, in this example, what we're going to do is we're going to take that linear, we're going to make a second linear layer that takes in that 128 examples and compresses it down to the vocabulary size.
I think so. The linear layer is the fully connected layer. So we have 2 of them. Basically the input layer and the output layer. We don't have any hidden layers here. But before that, we have this embedding layer. Like, I'm exactly not sure what it does, but I mean, what we usually do is we send an input of size x, and x is converted into, let's say in this case it's 128, and this is sent to the next layer. It takes the whatever that's coming out from this layer, in this case it's 128, and then it gives us the vocabulary size or the number of classes if it's classification of something else. For example, if we are classifying cats and dogs, this will be 2, because we either need to show cat or a dog, right? So that is for image types. For text types, what we need is, whatever input we are giving, we need only the output of the next word that we want. I think that's what he's doing.
Now, it's
That's
important
my
that we're
guess.
compressing to the vocabulary size because we need to choose which of the 96 words is the word that's likely to follow. Now, this is just the initialization. No code has been run, no learning has happened there, and you notice this copious uses of views. So one of the hardest things you're going to have to work on when you work in deep learning is getting used to this notion of working with views and changing the structures of your objects as they come in. And we'll come out with an embeds. Now this embeds will be of size context and embedding size. So it'll be these 20 dimensional vector. It'll be pushed through the linear process, this linear model 1, and then we'll run it through a reloop. The output of that will then go into the second layer, comes in at 128, and will come out at vocabulary size. In case if you couldn't see this coming, because now what we have is an output that's of size 96, we're going to run that through a softmax. And the softmax is going to tell us which of the 96 words is the most likely, or the model thinks is the most likely to be predicted. And that will return our log probabilities. So this model, very simple, right? It's a 2-layer neural net. We have an embedding layer with 2 linear layers. Very small, and we can sort of forget about it for the moment. We can set it aside. So now, we have our model set up. Now the only question is, how do we actually execute that forward pass? Because we might have more complicated...
Let's actually paste it here. Okay.
logic. In our case, we don't, but we might. We're going to initialize a set of losses so we understand how well our model is performing as it goes forward. And in fact, let's finish this. So then we'll also create a loss function. We'll take the non-negative log likelihood, and this is the loss function that we're going to use to make sure that our model is moving in the right direction. Then we'll create an instance of our n-gram modeler where we pass it, again, the variables that we needed, right? We needed the vocab size, so we've got the length of the vocab, that's 96. The dimensions, the embedding dimensions, which we've defined as 10 above, and the context size, which again is 2, which we've defined above. That's all we have to pass the model. Again, at this stage, the model hasn't been run, no data's been exchanged. We've just initialized the model. We've executed this initialization step, but nothing from the forward pass. And next what we'll do is we're going to set up an optimizer. Again, in this case, they're using stochastic gradient descent. They're passing in the model's parameters into the optimizer with a certain learning rate. Let's just take a moment here and bring this together. Okay. So now, we're almost near the end. It's pretty impressive, actually, that for as complicated as example we're only at 80 lines of code, and that's with the copious comments that they make. So now what we're going to do is we're going to do 10 epochs. And the 10 epochs are going to start, each epochs will start with a total loss of 0, because we like to chart our loss as it goes over time. And we will take, for each of the n-grams, now remember our n-grams were our word pairs, so when and 40 leads to winters. But we can't put in when and 40. So what we're going to do is we're going to, for each of these context.
So we have to create a model, which is the Ngram language model, I guess. So the three parameters is and the context size and the embedding dimension. It's reverse. Okay, because embedding dimension is the first one. Yeah, so we have this model. So it has the first layer, which is embedding, and you can see we have 97 words in our vocabulary, and we are the dimension is 10, and the first fully connected layer takes in 20, gives out 128, and again it takes in the second layer, or the output layer takes in 128 and gives us 97. So 97 because we have 97 words, and the output is any one of that word. I guess okay, let's move on.
And target for each of the contexts, that would be when and 40. We're going to convert those words to their numbers, numerical representation right here. So we start with when and 40 and then winters. We come down here and we're going to create a tensor. And the tensor is going to take all the words when and 40 and convert them into their index, whatever those numbers are, the two number representation.
So we are going to do epoch. So each epoch is an iteration on these words, and we will train that model for n number of times. We'll calculate the loss, and we'll do something called the backward pass. To, as I was saying before, we have to update the weights. So in order to do that, we have to calculate the loss, which means how far is the output from the target output, and then update the weights according to it. We have to do this iteratively, like 10 or 20 or mostly more than that if you take the production models, and then we calculate the loss each time if it's iterating. So traditionally, or the condition for a good model is that the loss should decrease for every iteration. So that's the goal also when you are training any model. So yeah, let's write that for epoch in range of 10. So we are going through every word, not every word, every word in this n-gram. So this is the n-gram, if you remember. So yeah, this one. So that's the n-gram, and what we're doing is we are creating a tensor out of it. So as I was saying before, we will not be sending the word itself as an input to the network, but we'll be sending the word which is converted to the tensor form. So that's what we're doing here. So we have this word to index also. Actually, what does that do? So we have this word to, that is the, I guess, representation of words in numerical forms. Yeah, this one. Each word has a number which you're seeing. Yeah, so we'll take the number of, so for each word we are taking the number and then putting it into the tensor. That's what we're doing here, but I guess this is a bit outdated for W, I guess. No, okay, I'll just, so we'll go through every so yeah, I'll just say what we are doing. So we are each word or each item in this n-gram is a tuple, right? So it has two entries. One is the first two words, and the third is the target word, or the word which is the output of these two input words. So we are going through every n-gram element which is a tuple, and we get the first one which is the array of two elements, and the second one which is a target and it's one entry. We'll take that out, and we'll create a tensor out of it. I don't think this should work because as I've seen before, torch.tensor doesn't exist. Okay. I think, okay, we have given the D type. So usually we have this torch.long tensor as well. So if you do that, we don't need to give the D type here. Yeah. You can see what we're doing is we're creating an array in context. So whatever, yeah, in this word 40 and when, we take the numbers of these words and then create a tensor. For in this case, it's 7 and 9 and 79. So that's one tensor, and we do put that in context indexes variable. And yeah, we have to call this model.0grad because we don't want to calculate the, we want to reset the gradients before calculating this. And then we will forward pass the, we'll call the model directly. So the model is this. So we could have called this directly, but this is itself a class, so we can call the model with the inputs. I think the log, let's say lg is model of what of the input, which is this. So our goal is to send these numbers as a input, and then see whatever it comes out, and we have to say to that network that this is wrong, you have to output so and so, let's say x as output if you are getting these two as an input. So that's what we are doing here. We are taking the loss function, which is, where is the loss function? Yeah, here, which is another loss. Let's say yeah, it's basically a loss function. So we will call that function. So we will send whatever output we got, and we will send whatever the target output is, because we want to calculate the loss between these two. So you calculate a loss when you know the correct answer, and you know whatever answer the model gave you, you compare it and then calculate the loss. So we do that. So let's say loss is loss function. I think this is loss function, right? It is loss function. We are going to compare two things. One is the LG, the output we are getting from the model, and the correct answer, which is actually the target, but we don't want to give the target as a comparison for model. So whenever we are dealing with words, we have to remember that we are going to give the number of that word and not the word itself. So we have to create the tensor again for for that target, just like we created for the input. So we can say long tensor and word to index of the target, right? So this is the loss, and let's print the loss. Right now we are not doing anything but just calculating the loss. The machine is not learning anything. In order to learn something, we have to do something called backward propagation. So that is how, I mean, if you are not aware of what back propagation is, I think it's a very popular concept in neural network and most important part of neural network, because it is how the neural networks learn, right? The backward, what it does is it sends the loss or whatever loss we have calculated back to the layers, and it reevaluates the weights between the neurons. So let's try running this. The loss is not stable. So this is the loss we are getting. So it is also a tensor, right? Let's try something else. So we'll just finish this. So we're also we need the optimizer, right? So this is basically adding the loss to the total loss. Let's say total loss 0, and then loss, let's say losses is an array. We have to have that, and we append the total loss, and I think we should reset the total loss to 0, I guess. I don't think so. And for everything we will print the losses. I think we can just print the losses at the end here. Okay, so this is the total loss of each iteration. So we have 10 iterations, so we have 10 elements here. It is not quite stable because we have 522 for 1000. It's actually quite increasing, but let's try to do this. Let's reset this. You can see the loss is decreasing. The total loss itself is decreasing from 520 to 517 to 515, so on to 498. So the loss is decreasing, which means the network is learning something, right? So let's see.
It's going to pass that in as a list. That list is going to be converted to a tensor, a Pytorch tensor. We'll have to deal with a lot of stuff like this later, and that will end up with our context indices. We will now zero out the gradient. Now, I'd like to point out that one of the important things here is that we are going to, at each step, zero out the gradient. So there's a bunch of stuff here that you just do time after time, regardless of the context. These are functions that aren't going to change. This step of converting your raw data into a tensor, you're going to do every time. This step of zeroing your gradient, you're going to do every time. And then what we'll do is we'll pass the value through our model, and we'll run this model for the context IDs. So note, this will return us a set of log probabilities. Notice we have not done anything related to the labels yet. But now we get a list of 96 values that comes out of this model, and those 96 values correspond to how much our model thinks each of the following words of the 96 should be the one that's the most important. Now we'd like to see how good a job it did at sort of making those assessments. So now we have our loss function, of course, which we've defined up here as the non-negative log likelihood. And now, for the first time, we'll take those log probabilities and we're going to pass in is word to index. These are the values that we've just generated from our labels. So now we have a label, it's the next word, winters in this case. We'll convert winters into a number, numeric representation. We'll then calculate the loss function, we'll get the loss. How far away were we from the right answer in terms of our list from the actual answer?
Yeah, that was what I was saying as back propagation as
Each
well.
of these steps,
we'll calculate the
you're
loss.
going to do every single time. Every model that you run is going to basically run it.
Yeah.
And then the next two you're going to do as well. You're going to then take the loss and back propagate the mistake across the whole data set. So you're going to back propagate the loss across the model, and you're going to run an optimizer step. Now what's a bit confusing for us is that these effects, they're almost like side effects, they're effects that happen inside the code that aren't directly called. You wouldn't know unless I told you that this step, this loss dot backwards, was going to update the model, but it does. You wouldn't know that this optimizer dot step would have an effect on the whole process, but it does. And that's because Pytorch has worked really hard to abstract away a lot of the complexities and make things a little bit easier. Are going down, and this is the important point.
Yeah.
Your model may be overfitting. Your model, in fact, we know our model will be.
So, if we are asking for one word, the weight of a word, so it gives us 10 dimensional tensor, not 10 dimensional but 10 entries from a tensor. So what is this? So this is model.embeddings.weight. So each word has a weight, and because we are giving here the embedding dimension as 10, this has 10 entries here. Okay, let's see.
But the real question is your model learning? So if we'd set this up and we hadn't seen that the losses 525, 523, 520 are monotonically decreasing, that is, for every step we're moving in the right direction, you might wonder if, but another example, if you saw at the beginning that your first loss and your last loss were very much the same, you might wonder a couple of things. One, does your data have a problem? Or two, do you actually need to go back and double check your code because you've introduced a mistake? Both are possible. And then finally, what we'll do, and this is nice, embeddings, one of the great values of embeddings is the ability to visualize the representation for each of these words. Now, in our example, these words don't have a lot of intuition, but in other examples, they very much might. And so here, what you can see is that we have the 10-dimensional tensor that describes the word beauty. Again, this is something we can touch on later. The purpose of this right now is to walk through this example and make a decision, sort of understand how the code is actually executing. Now the assignment, the next question for us, is we'd like to move, right now we've got a multi-class classification problem, right? We have a situation where we've got a list of 96 values, and we'd like to only choose, we'd like to choose the value that we think is the most likely to follow the first two. So the next video, what we're going to be thinking about is how we convert this example that we just went through to an example where it's a binary classification problem. That is, suppose you have two words and you'd like to know whether or not those words represent something. We'll be thinking about insults. So when certain certain words, certain word pairs are insulting and others are complimentary, and we'd like to have a label.
I think we have a part 2. So this doesn't make exactly sense, like what we're going to do with this 10 elements, but the thing is we are getting an output. The weights are being updated as well. If you run this, the weights are different and they are learning every single time. And I was just reading the chat. So you were working on some backend related stuff. What happened in between? I'm still working on backend only. And I was, as Abdullahi was saying, I'm not exactly into data science or machine learning. I was looking more into deep learning and neural networks, which required Python. So I started learning Python, and then I'm also working on Go also. So Python and Go are mostly what I do now. There are like things coming from the backend side as well. I'm not going to post more on data science, at least for now. So no, I am. That's mostly going to be backend stuff only. I think backend stuff, and mostly I try to do something from the implementational side rather than giving theoretical knowledge, at least from what I have, because that's what matters. From if you are in the backend, or I don't know about the front end, but backend side implementation matters. Even though you read system design or whatever you do, unless you're going to implement something, I don't think you're going to get the real understanding of how things work. So yeah, so summarizing it, next videos are going to be mostly backend heavy, and much later, like maybe 2 months later or something, I'll be also going into neural networks and deep learning as well. The reason I'm not doing now is that I don't have that much knowledge of those things, so I'm trying to gain as much as I can. And yeah, that's the reason I'm more into Python right now and Go. I am thinking of also doing Node.js streams, but still, let me know in the comments like what kind of streams that you want. We can do something like we can code out a full stack app on live. That would be interesting. Let me know in the comments if you're thinking of something. So yeah,
I wanted to also is a nice way for you to start to test yourself about what you really understand in these components, what would need to change in order for the code to work. So let's get started. We're going to start with exactly the same imports. Most of the time, we're going to be talking about the same things that we saw last week. The imports, tensor, the Pytorch.
Okay, so to give an intro, this video he is going to do something on binary classification, right? So basically we are going to see some output. So in this thing we didn't have any output, right? So this doesn't mean anything. So in this next part, he is going to give some output on binary classification.
Not a big fan of. I prefer to just look at compresses it down to a space of 1. That is, rather than compressing it down to a space of vocab size of all the possible words that are available, we need to know really just this single value that it's being pressed into. That's all we see for the initialization. Now for the forward, we again will take our inputs, the value that's coming in. The embeds will come in, and they'll come in, we'll press them through that first embedding. We'll look at the output of the linear layer, which we take the size that we're compressing to cross entropy loss. We're using a binary cross entropy loss to make sure that we're doing things correctly. And then we'll run and initialize our model with the size of the vocab, the embedding dimensions, and the context size. We'll run the optimizer in exactly the same way, no change here as well. And then for 10 epochs, we'll run through and we'll generate the total loss. Again, we'll take the context and the target out of the data, exactly the same as the last time. We'll run our torch model where we take each value that comes out of the context, so each of these words, converts them into the word index to generate the tensor.
Okay, BC loss is mostly for binary classification.
We'll then take this model, pass in the context IDs. Again, I've left this log props here just for clarity code, so we don't have to chase down other variable names. And we'll run our loss function, the loss backwards, an optimizer step, the total loss, and the loss append. And then we finally print out the losses. Things have not changed at all. And this is actually really quite important. We have made 3 changes to our code, substantive changes. We've changed our output, we've changed our softmax to a sigmoid, we've changed our binary cross entropy loss. And those 3 changes are enough for us to convert from a binary problem to a multi-class or from a multi-class to a binary. So it works in both directions. I like this example because it introduces this idea that we can start to think about the question that we're really interested in asking. Again, we're very interested in examples. In this case, it seems like in the first NLP example that we're really interested in a sequence prediction problem or a task along those lines. But more often than not, I find these sorts of binary classification problems are more useful in typical industry applications for sort of highly applied work. Sentiment analysis is easy. If you had a list of individuals who were frustrated or who left a company after a period of time, maybe customers who stopped working with you, you had the transcripts of the emails that they sent in, you could convert their emails into this portion of our tuple, a list of all the words they used in the last email that they sent, perhaps before they left, and then a 1 or 0 based on whether or not they would be leaving. This would be a great way to very quickly identify problematic words or personalities or attitudes that would lead to bad results in terms of your outcome. The binary classification problem, is a customer going to leave or not, is one that we see in a variety of different places under a variety of different. We're going to take one more step forward in terms of our thought process. We're now not going to think just about embedding.
We have to change the loss. I'll just change that. Where is it? So for binary classification, we can use BCE loss, I guess. And we are going with the output size of 1 because we only need to know what is what.
A single type of embeddings, we're going to introduce the notion of 2 embeddings. So the idea here is that you'd like to have both a notion of a speaker and you'd like to have the things that they say. So the thought process here comes from, if I'm talking to one of my friends and I tell them that they stink, that actually might be something that I'm joking about. So if my persona is that I'm, your good friend, you'll hear me rib you and make fun of you quite regularly, I would expect the same. Meanwhile, in the capacity of a professor, if I tell one of my students that, it would be a very, very insulting thing and something that would be inappropriate. So we will start thinking about the idea that we have individual personas or people, who they are in your life, your professor, your friends, your brother, your mother, your sister, and how, whether or not what they say, even though different people are saying the same things, they have different contexts. And we know this is true. We know that there are things you say to your friends that you wouldn't say to your boss, and vice versa. But at the same time, what we'd like to do is we'd like to have an embedding space for both the speaker, and then we'd like to have an embedding space for the words. And those two different separate embedding spaces are going to be the sort of the foundation that we move forward as we start to build up some more of the complexities of how you structure Pytorch code. So really, the next few, this video and the next video will be a little bit more about the conceptual thought process. And once we hit that step, then we're going to move into building an example that actually looks like final Pytorch code that you might actually use in production with all the sort of bells and whistles. Maybe not all the bells and whistles, but enough of them so that you can have code that works in production and it seems pretty reasonable for others to come along and work with. Anyway, so get started on that. Try to expand our data set to include a speaker, and then the words that they utter, and whether the words are compliments or insults. Remember, you'd like to have maybe 5 or 6 examples for each speaker, and maybe 5 or 6 different speakers. That's a pretty reasonable number to get started with. Speak soon.
So I'm just updating the previous code to accommodate binary classification. And P, we need to import numpy. Torch.sigmoid. Okay. These are losses. Again, you can see the loss going down from 1.512 to 1.476. Right. Let's just see what the weights are.
Hey everyone. Now the n-gram modeler again is going to import this neural net module from Pytorch, and we'll have an initialization. The initialization will take the same values again. Take the vocabulary size. In our case, that's 3. The embedding dimension. In our case, so a little bit, as I always do, and we can see very quickly that vast majority.
Okay, I think the weights are still very huge in number. I don't think we are doing anything right. We don't have any data itself. So actually let's thinking what can we do. Let's actually undo this. Okay. So we're getting another loss. Target 1 is out of bounds. Target. Where are we getting this? Okay, 71. Okay, we're getting the let's print the target, whatever it is. Winters. So we have this target. I think this makes sense. So we have this 18. Target 18 is out of bounds. Why is it out of bound? Okay, because the output is not the same. What did we have this? Your hang vocabulary size. Yeah. This is not sigmoid, this is log softmax. And m would be 1. Yep, we have this loss decreasing, but what I want to see is the weights. Okay, then what's the weight of, let's say, 0? Yeah, so 0th word has these weights. Actually, let's go back, try to do something meaningful with this. So meaningful in the sense we have this embedding dimensions. Okay, so what we want to do is we want to input something. So now I can say maybe model of give input. So the input is going to be long tensor, and that's, let's say, 0 and 1. Let's say out, and we'll print that out. I guess because we are giving this okay, the size, input size for this model is context size into embedding dimensions. So you want to get an output. Is this okay to do? Are we getting 97? What's the length of this? Let's get the shape. So it's 1 into 97 because the 97 words. So okay, so one of these 97 words is the next word for this input. So for example, there is this, okay, let's see, when and 40, right? So let's give when and 40. Let's see, and let's see what the output is coming out. Word to index of when, word to index of 40. So we have to, I guess, torch.argmax 89 out index is we will print the vocab, I guess, of out in, not vocab exactly. What is vocab, by the way? Yeah, vocab of so I want the 89th word at least. Word to index uses the number of that word, so we'll need the reverse also, right? So we need the index to word also. So we say index to word index and if you say index to word yeah, so if we get oops we got 71. Why can't we have 71 in this? So that's not a list, maybe that's why. Oh, we are getting okay. Out in is the it's a tensor, right? How can we get the value? I think it's 0 or maybe let's say vars of outer. Nope. It's a method. Let's see, get a value, get the value of tensor Pytorch dot item gets it, so we can say dot item. I think we can say out in dot item. So we get praise once, we get praise twice, we get thou. So we are sending when and 40. The answer should be winters. Let's do some more iterations then. Let's do 40. Yeah. Okay, the first word is when. The first word should be 40, right? And the when should be uppercase W. So we need winters. We're getting Thai. 40 and when. So uh, I'm actually doubtful of this. Oops. Let's print. So we have all eating in more. So is this valid? Because let's do word to index then and then print it now. So if you say much, it is 0 here, but here 0 is all eating, so it's not exactly what we want. The data is like not consistent, but we're doing the same thing, right? We are indexes through word for I comma word and enumerate of this. So vocab is a set of this. Let's write this. I to word. Yeah, now it's getting the same. So 0 is beauties, 1 is within, count is 2. Yeah. So now we should print 40 and when. So let's print when 40. Yet and let's remove this. Get thigh. But we need 40 winters. So here we were giving 40 when winters. Winters 40 shall. Let's say fair child. Why are we getting thigh so much? Okay, maybe we need more input. This is very, low input data. But I think we get the idea of how this is working. Yeah, so this is most of it. This is what I wanted to do today. I think it's pretty late. I'm going to sleep. Refresh. Okay. Thank you for watching, guys. So do subscribe on Twitch or follow. I don't know what it is. And do hit. I'll just put my YouTube link here if anyone is watching and wants to know. I think it's on my Twitch channel as well. So yeah, thanks for watching and good night.